Thank you. So first I will say who I am. I'm a security researcher in positive technologies. I play in CTF and have some experience in exploitation and binary analysis. Today we were going to speak about Linux ASLR. We'll take a look how it is implemented and find some weaknesses. We'll take a look much closer on GNU Libc, and we'll find a lot of interesting weaknesses of it. And I will also say some words about Linux kernel patches I prepared for some of what I found. So let's start with the basic things, just to make everything knows about it. So address space layout randomization is a mitigation technique that was made a lot time before. So it's based on idea, let's add some randomness to the address. And basically this idea has different implementation in other operation systems. And there's no good approach about what exact address we should take and how we can get this random and so on. So that's why for the last years you may found a lot of different researches about address space layout randomization in this or that was compromised. So some evolution about address space. It was introduced first in Linux in 2005 year, and you may find a good description of it on Xrl site. The link is provided. And of course, good things was made by Pax team and GR security. The last patches was attended to offset to lib attack that allows you to use offsets to lib from binary to bypass the ASLR. And this one was fixed. And the last work I want to point before we go next is ASLR and GNU that covers something we will talk today, but there are still no patches provided. Okay, some basically known techniques of bypassing ASLR is, first of all, is information leakage. When you can get some pointer from a vulnerable application and just use it later or forever you want. Another one, techniques is out of bounds. Of course, when you have some static array or dynamic array, don't matter, and you can address from it from some, I don't know, input. Another one is a weak implementation. Of course, good example was an AMD bulldozer that allows you to find the stack easily, link provided. And side effects, of course, this is almost everything knows already, I hope. Oh, it's a lead time, by the way. So first of all, let's take a look on how does current ASLR works in Linux. We will take a look on the maps. It's, if you know, it's a file that allows to show current layout, current mappings in Linux. And what we will see, that behavior would be the same for any other process. And we will focus on x86 64 bits because it's modern and so on. So first of all, you will see the binary image of, in our case it's less, but it could be anything else, and it looks fine honestly. So this, what I want to point here is that here is a BSS section of static arrays, global arrays, which are not mapped as binless itself, but it's mapped by kernel. So I think it's important to know that this thing exists. So next one is heap. Heap is just near the binary, and later we will see why. And right now, yeah, it also looks fine. What doesn't look fine is libraries. If you take closer, the libraries are going one by one, and they just clue to each other. And this because libraries was loaded by GNU Libc and loaded with a map system call who work like this. So what we need to know about it right here and right now, that a map system calls works like this, and that GNU Libc do the loading of any needed libraries for your process. Right here I want to sorry, I don't know. It's bigger. Okay. I will fix it, okay, later. Yes. First of all, from the exec-v system call that creates new process in Linux, happens the following things. Current mapping is removed from the process, and it starts with creating a stack region. After stack region, operation system chooses a map based with a special value that later will be used to make any map system call, to make any address from it. So this is somehow a higher border at which a map will choose address. After that, it makes a binary. The formula you see describes it, and it starts with a loading interpreter and makes it to run. Yeah, and heap is only 32 megabytes from binary. Yeah, this is just a basic things. You may know it already. So right now we will speak about how exactly a map works. A map system call inside of Linux kernel works with a structure that named VM area, virtual memory area, and it describes start, end, and page access permissions for this VMA. It's what we really need to know about it. All other fields are not necessary right now. These structures are organized in doubly linked list. It allows to find neighbor VMA in kernel. And also it's organized to red-black tree. Here the key of a tree is start of segment. And this is how Linux kernel helps to search the VMA according to the address. For example, if you have a page fault, you go through this tree and found the exact VMA and make a call, for example, to load pages, exact pages for these mappings, and so on. Yeah, and also this complicated structure used for finding, for choosing memory address. It keeps gap between two VMAs, and also this is an augment red-black tree, and it keeps gap that is calculated like a gap between a neighbor, between a previous VMA, and gap of left and right subtree. So how the algorithm works of choosing address, it just trying to use and find a maximum address that have a suitable length. That's why you see that all libraries goes one by one. So this is an important point because we will use the exact algorithm how a map chooses it. I want you to understand it. So, sorry. Now let's talk why is it bad. First, and it was already told in offset to lib attack, that all the signals are close to each other, and it means that we can easily make offset from one to another. And another one point is, if you corrupt something, you may affect neighbors' regions. Also, if you leak address, you can easily compute the address of all other segments. We will see later how to do it properly. Yeah, and a good example I was found in the old 1913 years was a PHP model who has the error of reading lines, and if you make an extra comment, it interprets it like not a comment and continue to go on the memory, and you have the read order to the next segment. So yeah, let's see how this issue is deep enough. To do so, I want you to understand how Linux process is created. When you call exec there, first kernel loads a binary. It loads the interpreter and executes an interpreter. In our case, it's a LD program. LD program do loading libraries. It's initialize different inner stuff and prepares different variables, allocating different objects. It runs constructors that were defined in the L file and do other stuff and run the exact application. So our plan would be to find some constant steps and try to use these constant steps to exploit everything. Yeah, and what I will use is the fact that any program have such property that you can control execution flow somehow. For example, in any attack, when you, for example, use use after free vulnerability or other else, what you do, you making some flow to make all objects be in the memory like you want. So this one we will use to build such flow, and we will take a look what's going on the application from its beginning. And to do so, we will use a trace a map just to see what's calling and what's the layout. First of all, loading library order. It's what we see, because on the picture you seen from last prod self maps, there was libraries which are always in constant constant order. glibc doesn't use a system called uselib and implement loading of libraries by itself, and yeah, it has a constant order, and the algorithm is provided on the slide. That's how we can repeat this loading order. If you, for example, analyze some binary application, you can build the same loading order, and in theory you can make the same layout until the program starts, until anything will execute it. So this is a interesting point. Next step, why do we need it? There is a procedure linking table in the L file. It contains pointers to the libraries. For example, when libc links libraries, it uses this table to keep pointers to other libraries from function it needs. So if you, for example, leak address from one of functions, for example, it's usually what you're doing when you have arbitrary read. For example, you're trying to read .got plt and get the address of some function, for example, for offset to libc, and find the system, right? But when there's function wasn't called yet until that moment, it will contain a pointer to LD library, and it would be might be a problem because you need libc system and you have some libld. So here we can say that you can easily calculate difference between this function and get your desired libc system. You need only, what you need here is to know the size and offsets. To do so, you need the exact version of ELF files. And this ELF files could be easily gotten from Linux distributive packages. So here you will, for example, brute force only 10 times, but not much more. And things what you need to know that since version 7, for example, in Android operation system, there was implemented randomization for the library order. Next interesting thing that you might see on the mmap, that there was free allocations which are seated inside the libld. These free allocations, first of all, we need to say why these free allocations come there. Well, the answer is when Linux kernel loads something, it looks if there is a hole between two segments of ELF files, it's called unmap. And when it's unmapped, any other mmap allocation can be placed just in this space. And since Linux kernel was Linux kernel loading only binary and LD interpreter, this affects only these two. For example, in GNU Libc loader code, this call is made with mprotect to prot none. So, sorry. How you may use it? You may use it that, for example, if you have some mmap primitive or some memory that was mapped and you can use this memory to read or write out of bounds, you can bypass ASLR because you don't need to know anything else. You already near the libdl. You can overwrite the pointers and variables inside the libdl. Stack guard. Before continue, let me say about freed local storage. You may already know that freed local storage is used to keep some local variables local for the freed. So if you have another freed, you have another copy of this variable. And in our architecture x86-64, this is implemented with register fs. This register keeps a pointer to some special structure that's named TCB head, freed control block. And this structure points to stack guard. How does it work? This stack guard is a mitigation that works against buffer overflow and works like following. It just keeps a special secret value on the top of the stack and checks it when when you go from out of the function and you go to the epilogue of function, it checks this value to the talon value. And if this doesn't compares, if checks was failed, it called stack check fail and application will be terminated. So what's interesting here? So one of these free allocation was a TCB of main freed. And this means that you know the location of the stack cookie. And how to get there? You just need to map some small value to get under this TCB and some big value to get above this TCB. So once again, if you have some out of bounds from this mapping, you can easily, for example, read stack cookie. It's one of possible. Also, it is possible to change other fields of TCB which are also interested but not covered in this talk, but you may take a look also. How to get this buffer? To get this buffer, first of all, you can use a map of malicious file of, like I already said, right? And second one is a malloc with a big length. GNU Libc works when you call malloc with a big length, it sees and thinks and just call a map without using current heap. So if you have some map and heap overflow, you can use it to, for example, get TCB or get inside the LD and do crazy stuff. But that's not all. What would be if you create a thread and we'll try to find TCB of a new thread? Well, new thread is allocated with a map. Stack for a new thread is allocated with a map, and this new stack will be placed near the libraries. So, for example, if you have read out of bounds in the stack, in the area on the stack, right? You can change some values in the libraries. But there's a new TCB. Here's a call of clone. This is system call that makes a new thread inside the application. And you may see that it sets a child stack address and TLS address. And you may see that there is only 1088 bytes, 888 bytes below the stack. It means that you can easily overwrite stack cookie etalon value with, for example, this code. You just rewrite the real cookie with some value, and you just need to rewrite more bytes to rewrite the etalon value of stack guard also, and do the bypassing. What to say here? It really works. This is, you see the work of this code, and it has only 9060 you see how much bytes is here. Yes. This issue was not reported but was found and described in some blog of some guy in 2013, and this link was provided by Red Hat security team. They said, hey, we found that there was the same issue. Is it the same? I said, yes, that's the same. And they said, okay, but we need a bug in the Bugzilla to fix it. I think this one should be doing private, but okay. And Intel MEF was hacked the same way. Here's the point. Maybe you already know. They have a TLS on the bottom of the stack. So that's why I think it's somehow legacy from Minix, maybe, I don't know. But it's what we need to, fix. How to fix it? First of all, we need to remove write access from stack guard, because there's no any good reason to rewrite the stack guard, right? Next, we need to move stack guard separate to the separate region, somewhere out of the stack of the thread, and this place should be random enough to doesn't allow any attacker to get to find this address. And another one good idea to have a new canary. Since we use FS register for any thread, we can generate new canary for any thread, and only Linux can do it, because, for example, in Mac OS X and in the Windows, stack canary is kept in the static variables. So I don't know, I think it's a really interesting idea. But anyway, this bypass techniques is your day for now. Next, let's call malloc from the thread we just created. If you call malloc from the thread, you will see that a map is called, and this map just creates a new heap. And what does it mean? It means that now your heap object is very close to the stack, to the libraries, and so on. much closer than original heap. So if you leak something, you can calculate the address of libraries. But let's see on some proof of concept. If we take a look on the result of this code, we will see the difference. And where is this difference going? The answer is when libc allocates a new heap, it uses alignment. It doesn't allocate just a map and that's all. It's a map 128 megabytes and unmap the part that is not aligned. So you may see that there's possible heaps. Count possible heaps has power of 2 to 22. And if you, for example, tries to do it from the application beginning, just from the beginning, just call pfread create, and inside the pfread create you call malloc, you will see that only 2 in 14 entropy here, and it's very easily to guess. It's a really small value. Vendor says that's not a vulnerability, it's an algorithm constraint how malloc works. So I'm disagreeing with them. I used this simple Python code to get some histogram of these values. It just runs my C code and just remembers the addresses it returns. And here's the small code, just malloc and printf. And you may see that POC makes this result. This is just proof of concept. So next interesting thing. One of interesting flags of a map is map fixed. These flags allow you to fix the address that you request. For example, if you need to map to allocate memory in the exact address. And there is, in manual, there is some point that if you have existing mapping there, it would be discarded. The problem of it, if you have some primitive that can re-map memory, you can do whatever you want, honestly. And this problem discussed already on the LVM.net articles, but with a different example, I found another interesting example, honestly. So here's ELF, and this is description from the ELF specific file. And you may see there is a description of ELF segment, and there is a point that they should be sorted on the PV header. But not kernel, not libdl check this at all. This means we can make different order, and let's see what happens. I have some demonstration. Here is I used special, exploit for LDD utility that is used to show the libraries of some binary. And also I have some fun with radar2 framework. This one is how it works. It's just example how it usually works. And now I prepare my exploit. You can see then inside the LGD I executed my cat etc passwd. And also I crashed the Rabin utility. I think you love it. Yes, thank you. This slides demonstrate the same. I made it before I used exploit. How does it work? It has only 3 segments. One is headers, read, write, doesn't matter. Second has sum of first and third. And third is just another one segment, just a padding. So how do Linux kernel and GNU Libc computes, how do they load anything? First of all, they compute total size of ELF file because they need to know it because they want to allocate enough memory. They do it only with counting first and last segment. So here's an error. They just take last segment minus first segment. And that's how they compute the total size. And here I just remap with the third segment, I just remap the libc that comes just after my libelf. So here you may see libc and libeval. So I just, with my libeval, I just rewrite the libc code, and since a map function is inside the libc code, it rewrite, and when it goes back from system call, it just started to execute another code. So, well, I don't know manual about LDD. In the manual about LDD, it is said that sometimes LDD may execute code, but that's why you shouldn't use it in the malicious files. But you know, there's some difference between might execute code and will guarantee execute code, right? But anyway, community thinks this is not a security issue. Just try to send my exploit to your friend and ask, hey, man, how many libraries need to be for this code, for example, for this ELF? He will type LDD and have some kind of exploitation. It's like XSS for binaries. Okay, what's the impact? The impact for it is copy-pasted code. Why copy-pasted code? Because, you know, radar, because LDD, GNU Libc, LD, and because Linux kernel had the same pain. They didn't care about PV address. So I think you may find much more projects that do the same loading. And especially in some different obfuscation and anti-emulation tricks, you may use this approach. Another one thing in binary analysis tools like Rabin and Radar just crashed. Maybe some online tools works the same. I never tested. But let's go next. Next thing, what I found was a memory cache. Well, libc keeps cache of the stacks it allocates and the threads and the heap it allocates. So each time you call pthread create, it first checks that there is a stack cached in the list, and if so, it will return this address. The same for the malloc from the thread. What does it mean? It means then if you leak it only once, you have a good chance to take it for another thread. So even if thread is finished and you have leakage, you can use this address later. It's easily bypass of ASLR. And also initialized volume. Here's the code that just do this proof of concept. It do malloc, it sets some value, it prints everything. And it sets only if it's first time executed. As you can see, the same values. Absolutely. There is no mmap call between this. And here's the response of security team. ASLR is a post-exploitation mitigation measure. Honestly, I didn't know. So next is address space layout and randomization. As we already said, it is easily to build the same order of libraries. It is easily to repeat the algorithm of how Linux kernel chooses the address. So I did the same. I just implemented some small Python script who chooses the max suitable size and parses load libraries and do the same layout before we go to the main. And also we can go deeper, and for example, if we use a trace utility to analyze some binary, and we will see that, and if we see that from the beginning program makes some maps, we can also add there. And when we get some leakage, or we have read-write out of bounds, we just easily adjust this information, fix up this information in our layout and get the whole layout. I will push it to my GitHub and everyone could use it. So right now I think it's time to patch. We already discussed the holes, and how to patch the holes is quite easy. We just need to call prot non there. I already submitted a patch a few months ago, but never seen it. I hope right now it will take more attention. Next one is a checking order in the ELF segments and terminate if it fails. And I'm going to provide a patch for a map choosing address. I'm going to make it random. So to do so, first of all, we need to make some list of gaps, because right now there is no information about the gaps, just only augment red-black tree that is not suitable for it. To do so, we need to keep some overhead. To don't this and don't spend a lot of kernel time, I just made a random choice. I used a current algorithm to get the max suitable address, and I'm starting to walk the tree from the lowest address and randomly choose suitable regions. And that's how I choose a really random region and take some page in this region. Very simple, honestly. I've tested this patch on the current Ubuntu, and I really like it because libraries are hard to predict. TCB is somewhere outside the scope. You will never find it. And system works fine. I'm even tried different browsers. I watch YouTube. It works. So can you feel the difference on these pictures first? Before it is current randomization and after is a new one. Of course, the ideal case how to fix this issue would be to take a look on each different type of segment. For example, you have a fried stack, so you need to have some separate regions for that. And you have libraries, you have some separate regions for libraries and so on. But I think it's complicated, and maybe someday we will see this approach. So what's the limitations? Right now the limitation is it works only with 64-bit architecture, because in 32-bit architectures there is no so much virtual memory. But I think it could be done just decreasing the entropy. And of course I've added some overhead to because in worst case I will need to visit whole tree from the one list to another. But it's security, right? Yeah, and before I finished, I found one more bug in Linux kernel. It's quite simple, but anyway. So when I just first executed it, application will crash randomly. And it was with the reason of EAPERM, like no permissions. And this reason usually happens when you trying to map a file that you don't have access to. But in my case, I got this error even inside the Linux kernel allocations. So the reason was about a map min address. This is a variable, system configuration variable. You can change it as administrator from system control, and it do the following. It have some hook that checks on any map request. It checks that you cannot allocate less than this value because it's prohibited by the system. The error was because Linux kernel, when trying to call in the function of searching address, doesn't use this variable and use just hard-coded value for k, like page size only. So the reason if we choose value less this address, mmap main address, when we get permissions fail. And interesting question about it, what happens if this value changing of this value will raise with the function that chooses the address, because it's two different functions. Like at one time you trying to find a suitable address in two borders, like less is a map min address, high is a map base, you're trying to find, and at the same time system administrator changes this value to some higher. And you choose this and you get EPRM because when you go out of the function that checks, chooses address, you go to the check that checks that this value less than a map min value. And it fails and you get EPRM. And nobody will handle it ever. So there's another one, DOS, deny of service vector. If you, for example, can somehow set this variable to the very big value, any request will happen with EPRM and nobody will can found it easily, because EPRM is going only of F control restrictions. So this is a question about the how I don't know how a map is designed, maybe how this hook's designed, as I think they need to change how they find the address, and they need to take account this value. So here's my conclusion. I described the implementation. I found many things, sorry. I found heap alignment, I found stack and freed caches. I reported it to the vendor. Also, today I said about problem of close memory regions. So if memory regions are close, and this is a problem, and I'm not first, but nobody cares, I think. Also, today I showed how the D was hacked and how to bypass stack guard. And I made utility for bypassing ASLR, and I patched the kernel. I will submit my patches very soon. I already sent these bugs to glibc tracker. You may take a look there. What else? Yeah, what's next? Well, the approach I made, I just take a look what happens on the process from the beginning. And the same thing could be done with the Microsoft Windows and Mac OS X, because I'm sure they have very interesting variables also. For example, in Mac OS X, when it loads much binary, it have different regions for RV and different regions for text. I mean for code and for data. But these regions are clue to other binaries. For example, if you call them up in the Mac OS X, you will see that all data of any loaded library lies just near the data of other library, but not near the code, but near the data. And the code is the same code near, but they are not in the one in the one segment. I hope you understand. Yes. And yeah, the good question is about 32-bit system, but it's already known that there is nothing to do. We need to use 64 bits. Yeah, I have some thanks to brilliant people who helped me while I did this research, who helped me in translation, in other stuff, and to this guy who made this picture. Thank you.
Anybody has any questions?
Thanks, nice talk. I just wonder, you said current Linux and you said Ubuntu. Which kernel version did you use?
I can't see. Sorry, can you please repeat?
Which kernel version did you test your exploits on?
Exploits for what? Can you please? Because everything is very connected, yeah, but I've tested on latest Ubuntu, for example. The same works on the latest kernel version. For example, you can just git clone Linux. You can build a new version of kernel and do the same. It will work because mmap is predictable and because GNU Libc doesn't care. So it works, it easily works. My exploit works, I don't know, it's perfectly. I just took a new Ubuntu and it works, I don't know.
I still think you should always mention the kernel version you're testing on, because Ubuntu is not a version, it's...
Yeah, I know, but it's much easier to say right now current, but yeah, in my white paper about this work, I used 4.1, what's the current version? I can't remember. No?
4.16, I think. I think it's 4.16.
Yeah.
Thank you.
No problem. I can take a look, honestly, because I have a clone of kernel.
So for the randomization of mmap addresses that you implemented, what is the worst case memory overhead? For example, when you're creating lots of 4K mappings, if you count all the extra page tables that you have to allocate, and what is the impact on TLB pressure?
Well, honestly, I didn't make any measures. I just checked that it works fine, and I was trying to allocate about 10 gigabytes or something like this. I didn't check the performance question because I honestly had no time.